thank you for this invitation, in particular to Thomas. I work for him. Let me go straight to my talk. So the second speaker said that it was lower technology compared to the first. So I'm obliged to say that I'm lower technology compared to the second. But I am really lower technology compared to the second, while the first and second were somehow very high top in that respect. So, okay, the title of the talk is somehow playing with words a little bit. It's 3 layers in quotation marks of graphene monolayer. That is really monolayer. When I say graphene, I mean that stuff which is inside the pencil that some of you may have in their hands. And GUP stands for Generalized Uncertainty Principles. Okay, I'm from Charles University in Prague, and I don't know this way. And this talk is based on a paper, which is on the archive, written by myself, these 2 pirates over here, Boris Iletich and Pablo Pais. Pablo is in the audience, and Boris is somewhere looking for a job, that's why I showed their face. While Salvatore on the other side is full professor then in Cagliari, so you won't need any help from this audience. I also point to you like some older work. One of the first in the line here is an ancestor of this paper I'm going to talk about now, and you find it on the archive over there. There are too many authors there, so I didn't write all of them. The general framework of what I'm about to say is in this very recent review published by Universe in August or September, I guess, and on the archive since July. And there are 2 talks coming on later this week on Wednesday by another pirate, which is sitting next to me now here, and the pirate I told you before, which is Lucas Maldon and Pablo Pais. Okay, so Shadows of New Physics is the title of this section, and it is a sort of a recollection of I'm quite old, so I'm doing this stuff since long ago now. So I've been seeing these things happening again and again. And I try to say here a few words on the general, like established tradition, on trying to understand what happened there at high energy, in one way or the other, in what we have at our disposal here in our lab. So here by S, I mean, I'm in a strange situation, I'd like to point there. So by S there, I mean the action, for instance, of some high energy fields. In general, I indicate them with the capital Phi hat, okay? And we're looking for maps or way to express the lower energy theory here, and then correction. So epsilon will be some parameter, then the fields become unhat, and then you can go on and on in this expansion. Okay, so this is sort of very well established. So I referred. Some of you were talking about non-commutativity a moment ago, and 2 examples that come to the mind. And from the 90s, late 90s, early 2000, are non-commutative field theories, a la Seiberg and Witrin, for instance, where you define a non-commutative gauge field, and then these 2 gentlemen found a map between this high energy field and the lower energy fields. In terms of the lower energy field, one is the gauge field itself, and then you have these theta parameters. And then you take the action, for instance, one you saw before, which is fully symmetric, written in terms of these high energy objects, and you expand them, and you see the old Maxwell theory corrected by this extra term. And this extra term is typically, in this language, is something which goes like Planck length squared. Okay, so something very difficult to spot in our labs. But there have been, I don't know, thousands of papers trying to look for these effects in the lab. Another example, of course, that comes to the mind, again from roughly the same time, is colloidal constellated standard model extension. Okay, the action of the high energy objects, where you can write it in the standard model fashion plus corrections, and these coefficients there, they go like powers of the Planck length. These are the days of GUPs, so this thing is happening again, and all these things are, of course, connected among themselves. And the one way, I'm not an expert in GUPs, I have to say, but one way of looking at that is to define like high energy variables. The paper I'm referring to, or the approach I'm referring to, is the one put forward by DICE and Vagenas in this PRL of 2008, and then there are many follow-up papers after that. And essentially they introduced these high energy phase space variables, X and P, versus low energy, X naught, P naught. Later I will change my notation, but this is the notation they have. I will slightly change the notation. And they find high energy objects, this Pi over there, in terms of low energy momenta in this particular fashion. So something I'd like to stress right straight away is that the way you express high energy objects in terms of low energy is very important. And the fact that you have a minus or a plus over there is quite crucial. The two and the, all things you see over there are quite important to point to this theory or that theory. Some of the audience here know this stuff much better than me. So it is very crucial that you obtain this expression or similar expression. And when you don't, you have to, you have to ask yourself in which sense you are different and which sense you're equal, and so on and so forth. The parameter, again, is something related to the Planck length. Okay. Typically, there is a numerical object which I indicate like well, people in the field indicate with A to it. And the choice they make in this paper, there are some work behind. It's not something they do out of the blue, but somehow it's kind of out of the blue. They identify high energy coordinates with the low energy coordinates. Say, okay, they are the same, and the low energy do the standard thing, okay, xp equal I, while the x naught p naught equal I, while x and p do this generalized version of the commutation relation. Okay, and again, pay attention to the structure, because this structure has to be this way to have certain GUPs rather than others. So how this affects the physics? Okay, so the way or is like, just like what I tried to say in the beginning, in the general framework. So you take, let's say, look at the first line here. Okay, it's the standard Dirac equation. Okay, for a massive object with P. So you write that expression in terms of the high energy momenta that you have, and then you expand this high energy object in terms of low energy, and that's what you actually can measure in the lab. So this is the thing you have access to in your lab, and this is what you have to measure. This is, of course, the expression I wrote over there is true in any dimension, and the paper I'm quoting here, they refer to a two-dimensional version of that, which is something they can work out, they can solve exactly, blah, blah, blah. That's why they go two-dimension, and you see the standard Dirac, which is this bit and that bit, which is corrected by this higher derivative term. Okay, so very much in the spirit of what I told you before. This is quite fascinating, but what does that mean? I mean, can we actually put our hands on that? Can we measure anything rather than putting, again, constants, these parameters, and finding that they are 10 to the minus 48 or whatever, untouchable? Okay, so that's why now I go even lower in technology, and I go on the tip of your pencils, and I repeat the story, which is by these days, in the beginning was quite surprising, but these days is sort of an established field of research. Okay, this lattice you see over there is an hexagonal lattice of carbon atoms. Black and white is not because there are black and white carbon atoms, but because you have to distinguish between position. That's very crucial. So you have doublets. These doublets here are what is behind the doublet structure of the spinors. Okay, so this is all emerging, which is a word which I heard a few times in the previous two talks. And actually, the word I also heard that was not expecting is analogy. In both talks, you were referring to analogy, to BC and to gauge theory. So I'm an analog guy, and what made this structure very simple structure that, by the way, our condenser matter friend said it could not exist due to the Mermin-Wagner theorem. It should be unstable. That's actually over there and produced now industrially. Anyway, this layer, monolayer of carbon atoms called graphene, and it's been very much studied for application. It is very much studied for applications, but it became also quite popular among people like us. Why? Because of this. Because of the dispersion relation nearby what is called the Dirac point, which is just the 2D version of the Fermi point, okay? Conductivity and valence bands where they touch. Nearby there, okay, the dispersion relation look like that, and the Hamiltonian looks like this. So it's a Dirac system where essentially the main difference is the fact that the speed at which this excitation, this quasi-particle move, and it's not c, but it's 300th, 1 over that number by c. Okay, so it's much slower. Okay, but otherwise it's quite similar. And see how this thing became popular. Okay, just look at this insane number of citations. This paper by Gavin himself. It's about 32,000. And 206,000 access to the thing. So it became very famous. Among these, I dare to put my own work because with Gaetano Ambiase and our collaborators in Prague, some of which are present, we've been also using this analogy to actually probe sort of quantum gravity sort of things. But we were not, of course, the only ones. There were people among the discoverers here, Katzenelson, Self and Guy, the group of Maria Rosmiliano there in Madrid. So very popular stuff. All the papers you see over here, but the first one where they just reported the discovery, they are all about this analog interpretation. Okay, so making a Klein paradox in graphene, Aronoff bohm, and so on and so forth. But things are much more complicated, okay? Which is interesting. So from one point of view, some people took it as a clash of this analogy. You cannot go really beyond a certain amount of analogy. But you see, if you actually keep going a little bit in energy, you see that these things, this Dirac cone is not like so perfect. First of all, if you look a little bit closer, when you go up in energy, you see that the SO2 symmetry here is actually broken into a Z3, and something they call the trigonal warping. Okay, well, you saw some formula, you understand better. And then another thing that happens, you see the upper dome is much bigger than the lower dome. Okay, and this is courtesy of Pablo, Pablo Pais. If you actually if you take a snapshot of that thing close to this Dirac point, you see here is the trigonal warping. Here is the fact that the lower dome is reached much faster than the upper dome, and so on and so forth. Okay, and this capital VF is not the lower case VF. It's something that you'll see in a moment what it means if I'm fast. Okay, so this is the situation. Okay, can we do anything? Okay. How this comes about? How can we describe this? This part of my talk. Well, first thing you have to understand is that all I said about this simple dispersion relation comes about by considering only the near neighbors. So from each point you go only to the big, to the sharp grain circle around. Then you can, but you can include more and more effects from farther away neighbors. Okay, and this is if you actually do that, if you have a way of expressing the full Hamiltonian of the system completely in terms exactly. So if you take into account if these m, which are the number of neighbors you're considering, first neighbor, second neighbor, and so on and so forth, if you consider all of them, you have the exact expression. It's like somehow going into the full quantum theory of the story. And these functions are an expression which is given by this formula. These s's are the ones you saw before. These vectors here, and they're very simple to obtain, and you have all of them. And how do you get in special relation? Well, through this famous, the standard ways, which is the secular equation. You set that into zero. This is an extra thing, just to overlap in matrix. Don't mind too much about it. But all that analogy that made that thing famous among high energy physicists came from the fact that the F1, so the near neighbor story, has this expression. You expand this near that Dirac point, and you find what you say. Now let's go one step farther. That's what we've done. My collaborators and I. We went to the second step, m equal to 2, and we discovered a magic thing that for f equal to only, you can express easily f2 in terms of f1 through this formula. Okay, so the dispersion relation can be written now in this way. Don't get, don't think it's too simple. It looks simple, but it's not, because this F1 now has all contributions, and you have to decide at which level of precision you want to stop. And this is where the capital DF appears, which is slightly different. It's a little bit, so this is nearly 1, and we need 1.5 to go to the lower case. And here, you see for the first time my version, our version of A. Our version of A, remember the GUP version is the Planck length times a numerical factor. Here we have the lattice space times a numerical factor. So we define what we call supermomenta this way, and the special relation can now be written in this fashion. And you see that if you expand this capital P naught, you see this the trigonal warping. You see more and more effects popping up, and you can go and express the thing that you saw in the beginning. So, but the very same dispassion relation, instead of going this way, you can go the other way around, say, okay, I have this dispassion relation, what sort of effective Hamiltonian gives you the same dispassion relation? Well, that's one. This Hamiltonian gives you the dot dispassion relation, okay, which pushes us to define even one layer up, and define what we call hypermomenta. So, compared to the case of DICE and Vadenas, we have 3 layers. So the X and P, the X naught and P naught, and the capital P, X and P. In terms of these variables now, we can define yet another high energy Hamiltonian, in terms of which the dispassion relation become again the single one. So what I've done in mathematical terms, I've taken a non-linear realization of the momentum. So, and I made the thing linear again, and stick the non-linearity into the definition of P. Okay? Why so? Because now I am in a position which I tend to be similar to what happens in this high energy, low energy story of Zachary-Witten, of the GUPs, and so on and so forth. We have the fully symmetric story over here, in terms of this capital P, the hyper objects, with the Hamiltonian, which is the simplest one, and all the symmetries of the game are implemented. SU2 particle where symmetry is hypersymmetric. Okay? Then you have a middle way where you start breaking something because you add this correction in terms of P, but not too much, because still in terms of supermomenta. And then you break sort of everything. And you go down to this dispassion relation, which contains the trigonal warping, the upper and lower dome, and so on and so forth. Okay, and the Hamiltonian corresponding to that is too complicated to have it again into one slide, and it's this one. So I show you this Hamiltonian not because I'm nasty to you, but because if you look at this Hamiltonian, you knew nothing about what I said before. You would just not think about any Dirac or anything. You would not just even imagine that you can actually have this implementation in terms of nonlinearity, and this is what made this thing interesting for us. So if you stop at the circuit objects, you have the thing that made the graphene famous among analogists, and if you keep going and include this the supermomenta and the hypermomenta, you have a hope to go beyond. But I have to show you some GUP, and let's see. So the lowercase objects, you start off as standard quantum variables, so you know that they obey this algebra, okay? And what we have the capital P naught and the capital P. We have it. It's the physics that gives them. We have just taken from the definition from the lattice. What we need these 2 objects. Okay, and this has been quite complicated. It took us a few years actually, because in the beginning we didn't realize we only have formal objects, and now we have this clear expression. So to summarize everything into one slide, that's what we have. We have the world, which is the thing we want to then refer everything back to. So we're going to make measurements here, because this is where people do experiments and so on and so forth. Then we have a middle layer, which is the super world in terms of these variables capital X naught and P naught and capital P naught. And then we have the hyper world, where everything is back to symmetry, full symmetry. And depending on the way, we call these things ladder, you do things, you can have various situations, and at each of the situations we have the transformation. I mean, we have these variables. Okay? So the most interesting one is the one where you see you go you go 1, 3, 7. So you go 1, and then you go 3, and then 7. It means you go GUP all the way. I say GUP, but actually what I really do, I just deform I didn't went to the delta X, delta P, but just the commutations, okay? But anyway, the GUP all the way is quite interesting, okay? It's interesting because you have GUP all the way, and it's even more interesting because you need to do nothing to the coordinates. I mean, the coordinates are just just the ones you had from the very beginning. So it's the simplest thing you have to do, the most natural. You just keep the same coordinates all over the place, And you have, in the first step, the first ladder, going world, super world, you get this bit weird, I call it GUP, but you see what I mean, okay? With this F given in this fashion. With F has a sort of nice property, blah, 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 but it's not like a standard one. I know already that some GUP people are looking into that and see if they can recognize anything familiar, but they will recognize something familiar in the older step. They won't recognize anything familiar in this FIJ, but they will in the Pauli FIJ, which is the step you get afterwards, which is essentially an expression very similar to the one we saw before. You see, the one of DICE10, but then sort of corrected by this term. But then, as I said, this is only one way. You can go the canonical way. I mean, you can keep canonical variables all over the place, so you never get any GUP. But then the price you have to pay is that this capital X naught became quite complicated expressions in terms of measurable first case variables, which are lower x and lower p. Okay, and for instance, in going from the world to the super world, that's how these coordinates have to look. And going from the super world to the hyper world, this is how the capital X has to look in terms of the capital X naught. But then since you have to express everything back in terms of this measurable object, this is how complicated things get if you want to get canonical. That's why I said that the first ladder is very interesting, because you have to do nothing at all to the space coordinates. Okay, but even though this looks very messy, you still this is still something, because we know what's the correspondence. These coordinates, which were just upsets in the first analysis of the problem, to these ones. Okay, and then we have middle ways. We have middle ways, which is you do canonical in the first step, so it means you take these as capital X naught coordinates, and then you go GUP in the last step, and you find something which is very much similar to the Alidas variance object. Well, but not similar, but not the same. It will be the same if you stop at the first term, same sign, same structure precisely. But if you go to this last term here, they have a plus over here and a 3 over there, which we don't have. So this is what we get. And finally, you can go actually also in this ladder here, but the expression in terms of this G11, G12, GIG, in terms of all lowercase p are so messy that I just don't show them. We have them. Okay, so what to do with these is this final 3 very fast just part there in the slides. Well, all the fundamental in quotation mark, in the analogy sense that I mentioned at the beginning, all the fundamental physics that were serialized using graphene, using these properties of graphene, and let me say here, just incidentally, they can do a lot of stuff. You can go mass differ from 0, you can add gauge fields of the U1 or SU2 kind, you can add gravity objects. Okay, so this little lower the best stands for spin connection, and lower say the kappa stands for contortion or torsion, depends on the approach. So I mean, we've been doing that study now, it's already 10 years, we're looking into that. All the stuff can be GUP corrected. I mean, here I quote papers from some friends in the audience, right? Fabio Scardidi, again by Giuseppe Gaetano Luciano, Luciano Petruzzello, and Luca Buonfante, and another friends here. From these papers I learned, we even have a paper together with Fabio and Gaetano and Pablo on this object, on this particular application in 3-dimensional gravity. Okay, so we know that you can GUP correct physics, fundamental physics, of course, in this particular setting. So it's a Dirac field, it's a 2-dimensional, 2 plus 1 dimension. So you're not saying that you can do everything, but for this very well, framed. Oops, I do have one more. Okay, I know it's the same Hamiltonian I had somewhere. Okay. So all that thing can be done by simply taking this Hamiltonian and looking at which is there. I don't have to do anything at all. So that's sometimes difficult to explain to even to referees. To say, but you have to do nothing to the structure. Yes, but that's precisely why it's interesting. I take the structure, I just go a few steps away from the linear approximation, I do this redefinition, and I found that if I do that, I can realize some form of GUP. So that's what you have to do. So you saw the list of my time is over. You saw the list of experiments that people have been doing, or we think that sometimes are generic experiments only. Well, we can think of redoing that in graphene by adding these nonlinear terms, and this should tell us about how this phenomenon happens in a GUP environment. Okay, thank you so much.
Thank you very much for a nice talk. In the end, it became very dense, but it was good, very good. We have time for two very short questions, let's say, and then we have the coffee break. Otherwise, we will cut our coffee break.
No.
You have this nonlinear transformation from the x0 and p0 to x and p.
The capital ones?
The capital ones.
Only those? You want
only those for the moment. Is this nonlinear transformation unique, or could you construct other nonlinear transformations and get other GUPs?
Very good question. It's half fixed and half matter of naturality. Half fixed is how you relate capital P with capital P0. That's fixed by the physics. Everything in terms of the momentum variables is fixed by the physics, which is what makes this thing nice. You don't have to, it's given, it's the structure, and the structure of those functions, this F's over here. So you have the lattice, it's hexagonal, you decide how to do your this is a type binding approximation, and this fixes the capital not P. But for the capital X, for the coordinates, yes, you do have freedom. You do have a freedom, and you see already that you have freedom because I had at least two choices I showed to you, which were the canonical and the GUP choice. The fact which makes this thing interesting is that although you have choices, if you make the simplest of all, which is this one, you have interesting realizations. So, I don't know if that answers your question. Yes, we even have more than what I showed to you. For instance, we do have a sort of meager non-commutativity of coordinates, okay, but it's very unnatural, so I don't want to show it to you, okay? So we're still looking into that. If we can make any more natural sense of that, then perhaps this would deserve a separate talk, because, you know, it's a non-commutativity of coordinates, so it would point towards non-commutative geometry, something more deep, okay? So this way we wanted to select something that people would understand immediately, which is do nothing to the coordinates, this thing, and you have GUP, which is interesting, and keep canonical, which is also something quite natural. But yes, you have a variety of possibilities.
No,